having studied in detail the equations governing spherically symmetric radial perturbations around a spherically symmetric background model or hydrostatic model, we are now going to do the same, but without the restriction that the perturbations are spherically symmetric. We admit non-radial or non-spherical perturbations, and this means we are going now to the non-radial stability and pulsations equations. The strategy is very much the same as we did for the radial case. We start off from a spherically predetermined hydrostatic configuration, which does only depend on the mass coordinate or on spatial coordinate, but not on time. It's time independent and it's spherically symmetric. These are two important points for later. It's spherically symmetric and it is independent of time. It's a hydrostatic model and it satisfied the same condition and is constructed in the same way as before for the study of radial pulsations and perturbations. So we can assume that we know already, or the following quantities are predetermined and known. This is the radius r0 as a function of m, pressure, temperature, and so on. Now, in hitherto, we have only used the Lagrangian form of description. So we were always moving together with the fluid element, with the mass element. This is appropriate for one-dimensional systems, and it had the advantage that we could integrate Poisson's equation for the gravitational potential and give it in a closed algebraic form. This is no longer possible if we go to non-spherical perturbations. So what we have to do now is to solve the Poisson's equation explicitly. Well, of course, not for the hydrostatic model. This is a spherical symmetric model. But for the perturbations, we have to invoke the full Poisson's equation, which complicates the system a little bit. Not very much, but a little bit. It increases the number, or it increases the order of the differential system, which for some people might be difficult, but we will see it's actually not that complicated and does not cause so many trouble. On the other hand, it's now, as we are going to non-spherical, non-radial 3D perturbations, it's no longer advisable to use the Lagrangian description. It's more convenient to use the Eulerian description. So to say, we consider now our quantities as a function of radial or of position, and the position is our the position vector is our independent variable. So rather than writing r naught as a function of mr and rho and p as a function of mr, we replace it by function density as a function of radius, pressure as a function of density, and temperature. Of course, this can be done by simply rearranging variables in our models, which we have determined prior to the investigation of the stability and the perturbation. And we'll follow the same procedure as for the radial case, namely we linearize our general equations around this equilibrium. That means we take the mechanical and thermal equations as before, do the linearization as done for the radial case. Now we have to consider, in addition to the thermal and the mechanical equations, also Poisson's equation for the gravity. And we have to admit that we have now a three-dimensional perturbation. That means the perturbations do not only depend on the radius and the time, but also they depend on the angles theta and phi. It's convenient then to use spherical polar coordinates for describing the situations, and that means we write our quantity in the following form. So if we have a quantity q, this will now depend on three coordinates. This is a three-dimensional problem, it depends in spherical polar coordinates on the radial coordinates, on two angles theta and phi, and on the time t. And similar to the radial case, we split this quantity into a hydrostatic time-independent spherical part, which we know. This has been determined by stellar evolution calculation, plus a perturbation part Q1, which now depends on all coordinates. So this is the same procedure as before. This term is the same as for the radial case, and Q1 now depends not only on r and t, like in the radial case, but on theta and phi as well. Okay. Well, I have said this already. In general, Eulerian perturbation or the Eulerian picture is much more convenient than the Lagrangian one. Okay, so, well, I have to add some remarks about Eulerian and Lagrangian picture again, because perturbations themselves may also be considered as being Lagrangian or Eulerian. What means Eulerian perturbation? Then we consider, in the case of an Eulerian perturbation, we consider the difference of the perturbed system and the original system at a fixed position in space and fixed time. So the independent variables in the Eulerian picture will be the independent variables are the position vector and time t, and we consider a perturbed system and the original system. In the Lagrangian sense, perturbation means we consider a quantity in the perturbed Lagrangian for the perturbed mass element. We focus on the mass element. The independent variable is the initial position vector of our element, and then it moves, this mass element moves to a new position r, which depends on the initial condition, and now we perturb this element. That means we perturb also the new position. So it's moved to another position, and the difference between the position in the unperturbed system and the perturbed system is called the Lagrangian displacement. So because we change the radius, or we change the position vector, we change or we perturb also the position vector, and we have a difference between the actual position vector of the system in the unperturbed case and the position vector in the perturbed case. And of course, we relate the perturbed quantities also to the initial position vector of the mass element. So this the different ways of looking at the system, co-moving observer or fixed observer in space, transfers also to the description of the perturbations, and we have to distinguish between co-moving perturbations and fixed perturbations. That means between Lagrangian perturbations and Eulerian perturbations. This is pretty important to distinguish between these perturbations. For instance, if we take a star and we take its surface or its photosphere, and we require that the pressure perturbation should be zero, or we don't want to have the pressure to be changed. So which pressure perturbation do we really mean? Do we mean the pressure perturbation at a fixed space, or do we mean the pressure perturbation once we move with the perturbation, or once we move with the fluid element? This is different because in the case when you consider Lagrangian displacement, you follow, for instance, the distortion of the surface of the photosphere of the star. So what you require then would be, once you follow the distortion of the surface, you require that the pressure perturbation with respect to the perturbed quantity, perturbed surface, has to be zero. This is something different from sitting at a certain position. The surface of the star or the photosphere is distorted, and you ask that at this position the variation or the perturbation of the pressure should be zero. These are entirely different, and you have to think always which one of these perturbations, which kind of these perturbations have to be vanish or have to be continuous or what else. So it is not only a mathematical variety of describing the system. In some cases, one has to consider which one of the perturbations has to be considered, either a co-moving perturbation or a perturbation fixed in space. Okay. Okay, so we consider now not only two systems with two different descriptions, but we do also have, in addition, an original system and a perturbed system. So we have an unperturbed system, which is characterized by a quantity q or many quantities q, a position vector, either in the Lagrangian or a Lagrangian sense as a position vector depending on initial position vector, or in the Eulerian system just the position vector of a fixed position. And we have the perturbed system, q dash. The dash should denote a perturbed system. And we have, of course, in the Eulerian sense, we will not perturb the coordinate, the position vector r, but in the Lagrangian sense, of course, we will perturb the position of our mass element, which comes from the original position r0. Okay, so we have in the Lagrangian sense, an subscript L denotes in the Lagrangian sense, subscript E means in the Eulerian sense. So we have quantity q in the unperturbed system depending on initial vector r0, and a position vector which depends now, which is the dependent variable for the Lagrangian system, which depends on r0 and t. And we have a perturbed system. Well, in the Lagrangian sense, we perturb the quantity ql dash, which depends on initial position vector and t, and the position vector itself is no longer an unperturbed quantity, so we perturb the position vector and end up with r dash, also depending on r0 and t. It's much simpler in the Eulerian picture. We have the unperturbed system depending on independent variables r and t, and we have the perturbed quantity q e dash, which also depends on the position r and t. Now we have to identify the Eulerian and the Lagrangian quantities. Of course, the Lagrangian, this is the same as we discussed before, because the unperturbed system behaves like anything we have discussed in the previous lecture. Lagrangian quantity of the mass element, which is labeled by the initial vector r0, is equal to the Eulerian quantity of this mass element, which has moved from r0 to r. So this is the new position, or it's the actual position of this element. Now we have the perturbed quantities. That means the Lagrangian quantity, in the Lagrangian sense, quantity q in the perturbed system, depending on the initial vector, is now equal to the Eulerian perturbation, or the Eulerian quantity in the perturbed system, but no longer at r, because the position of our mass element has also been changed and been perturbed to reach the position r dash. Okay. Now we define two variations or two perturbations. First, a perturbation in the Lagrangian sense. This means the differences between unperturbed and perturbed system for a fixed mass element. Lagrangian always refers to a fixed mass element, so it's denoted by capital delta. Delta Q is the quantity in Lagrangian sense in the perturbed system minus the quantity in Lagrangian sense in the unperturbed system. So it's QL dash minus QL, both taken at the initial position vector R0. And we have the so-called Lagrangian displacement, because in the Lagrangian sense, the radius vector or the position vector is a dependent quantity. So the delta R measures the distance between the position of the mass element in the perturbed system and the unperturbed system. So this is R dash depending on R naught minus the original position vector R as a function of R naught and T. This is called the Lagrangian displacement. Actually, we have used this Lagrangian displacement implicitly already in the consideration of the radial case, but I haven't said that this is the Lagrangian displacement. It was the perturbation of radius. Perturbation of radius is nothing but Lagrangian displacement. Okay, in the Eulerian case, we denote the difference between the unperturbed or between the perturbed and the unperturbed system, so to say the Eulerian perturbations by A tilde. So these are the differences between perturbed and unperturbed system for fixed position vector. Pretty simple. This is QE dash minus QE at some fixed position R and T. Okay, what is the relation between these two? The question is, how can we calculate or how can we transfer or transform from the Lagrangian perturbations to the Eulerian perturbations? What is the connection between these two? And to find this, we use the definition and try to get a relation between Lagrangian and Eulerian variation of a quantity Q. By definition, delta Q is QL dash minus QL at the position R naught. This is by definition. Well, this can be written as, well, this can be identified now with their Eulerian counterparts. Well, QL dash is equal to the Eulerian value once we consider that the mass element has moved in the Lagrangian sense to a new position R, and in addition it is perturbed. So this has to be taken at a position where the element has been moved and perturbed. So it's now at position R dash comma T, and whereas here it's pretty simple. For the unperturbed system, the mass element has moved from R0 to R, so we have to identify the quantities in the Eulerian and Lagrangian sense at the Eulerian coordinate R and at the Lagrangian coordinate R0. Okay. Now, now we use the definition. Well, we keep this quantity. Now we use the definition of Q tilde, the Eulerian perturbation. The Eulerian perturbation was QE dash minus QE, both at the position R. So we rewrite it in the following form. Then this is it's Q tilde. This here is kept, and using the definition I showed you before, we can write it as Q tilde minus QE dash at the position R and T. It's just inserting here the definition of Q tilde and keeping the remaining terms. Okay. Now we expand the R dash. We expand R dash here in the second term. This is Q tilde plus QE dash at the position R dash, which is R plus delta R. This is the original, the unperturbed position of our element, and this is the perturbation. So the new vector will be R plus delta R comma T minus QE dash at the position R and T. Now, if delta R is small, we perform a Taylor expansion. This means this quantity here is, yes, this gives QE dash at the position R. This cancels with the second term, and the first term in the Taylor expansion is delta R times the gradient of QE dash at the position R. Simple Taylor expansion, and the first term in the expansion cancels. QE dash at R minus QE dash at R cancels. So this is the remainings. Now we have that we can, by definition, Q tilde is QE dash minus QE. We apply a gradient on this quantity. Then we may write this in following term. Gradient of QE dash is gradient of QE plus the gradient of the Eulerian perturbation Q tilde. Now we insert this gradient in here. Some question? Okay. Now we insert this gradient here, and we end up with some quantity QE. QE dash is gradient of QE plus gradient of Q tilde, but gradient Q tilde times delta R is a quantity of second order. We drop it. So we can write QE dash is simply the gradient of the quantity Q in the Eulerian sense, but for the unperturbed system. You agree? Okay, so we have found the following relation between Lagrangian and Eulerian perturbations. Well, it is delta Q, the Lagrangian variation of a quantity Q is equal to the Eulerian perturbation of this quantity plus the Lagrangian displacement vector times the gradient of the quantity Q in the Eulerian sense, still in the Eulerian sense, of the unperturbed system, because the Eulerian quantity is equal to the Lagrangian one, and we do not need to distinguish between these two. We can simply take this is the gradient of the quantity in the unperturbed system, which we know. For instance, our hydrostatic stellar model would then, or properties of the hydrostatic stellar model, would enter here through the gradient of the respective quantity. So it's simply delta Q is Q tilde plus Lagrangian displacement times the gradient of this quantity in the unperturbed system. Okay, once you mix both the Lagrangian and the Eulerian perturbation, and once you mix the Lagrangian and the Eulerian time derivatives, you have to be very careful, because these quantities in general do not commute. So d by dt delta q is not necessarily delta of dq by dt. So you have to satisfy or have to obey certain of commutation rules. They are not commutative in general. Well, if you remain within your Eulerian or Lagrangian picture, it's nice. Then they commute with each other. For instance, d by dt is the Lagrangian time derivative acting on a Lagrangian perturbation of quantity q. Then by definition of the left-hand side, this is ql dash at position r naught by dt minus dql by dt at r naught. And this, on the other hand, is simply the definition of the Lagrangian displacement of dq by dt. So that's fine. And similarly, we have for the Eulerian perturbation and the Eulerian time derivative, this is the definition of d by dt of q tilde is simply qe dash minus qe and the partial derivative. And this, on the other hand, is the definition of the Eulerian perturbation of dq by dt. So we can commute these operations, perturbation and time derivative. Similarly, also the gradient acting on an Eulerian perturbation by definition is simply the difference of the perturbed system and the original system in the Eulerian sense acting with a gradient. This is simply the definition of the Eulerian perturbation of the gradient. So in these three operations commute, Eulerian perturbations commute with Eulerian differential operators, and Lagrangian perturbations commute with Lagrangian time derivatives. Well, if you mix these two, then this is no longer true. So you can, for instance, you can write down the Lagrangian derivative of an Eulerian perturbation Q tilde. Then this is Lagrangian derivative of QE dash minus QE in the Eulerian sense, both differentiated with respect to the Lagrangian time derivative. Well, the Lagrangian time derivative may be replaced by the Eulerian time derivative by the rule we know. This is d by dt, or in Eulerian sense, plus the velocity times the gradient of QE in the Eulerian sense, minus the same quantity for the unperturbed system. That's actually an error. It should be not V tilde, but V E with a vector. Please correct this here. This is a misprint here. So what we did, we simply applied d by dt. Lagrangian is d by dt Eulerian plus velocity times the nabla or gradient operator. So this is the result. On the other hand, we can evaluate the Eulerian perturbation of the Lagrangian derivative with respect to time of the quantity Q. So we have to put the tilde over the entire bracket here. So this d by dt Lagrangian is d by dt Eulerian plus velocity times the gradient of the quantity Q. The Eulerian perturbation of the entire bracket. So by definition, this is the quantity at the Eulerian perturbation of that quantity. This means it's d by dt QE dash in the perturbed system. Also, the velocity and the value of Q has to be taken in the perturbed system, minus the whole expression in the unperturbed system in the Eulerian sense. So this is now we replace the VE dash, the Eulerian perturbation, or the Eulerian value, not the Eulerian perturbation, it is the velocity in the framework of the Eulerian prescription in the perturbed system. So this is given by VE dash minus VE is simply the Eulerian perturbation of the velocity. So we replace it by the Eulerian perturbation of the velocity and the velocity in the unperturbed system. So that's what is left. This is VE, and we have to add another term here. This is the Eulerian. It's the Eulerian perturbation of the Eulerian velocity, or the velocity in the Eulerian scheme. It's too many expressions and too many notations for this quantity. So to get off this dash, we simply use the definition of the Eulerian velocity perturbation. Eulerian velocity perturbation is VE dash minus VE. So we end up with VE tilde here, and otherwise it remains the same. So dQE dash d by dt plus VE gradient QE dash, this remains the same, and by applying the definition of the Eulerian velocity perturbation, we get this additional term here. Now we compare the two. Let's do it first the other way. this is simply this is the Eulerian perturbation of the d by dt q tilde, what we have here, plus the velocity times okay, qe dash is now replaced by the Eulerian perturbation of q and qe itself. So we have, this is v tilde times gradient qe plus gradient of the perturbation of q, Eulerian perturbation of q. So what we use is q here is q tilde is qe dash minus qe. So we replace the gradient qe dash here by gradient qe and gradient q tilde. So this is this term, and this here is by definition this is d by dt plus velocity times gradient d by dt minus d by dt plus velocity times gradient. This is simply d by dt in the Lagrangian sense of the difference between qe dash minus qe, which is d by dt Lagrangian by q tilde. Okay? This means now we have d by dt dq tilde by dq by dt perturbed Eulerian is d by dt of q tilde plus the velocity times the gradient of q, because this quantity here is of second order in the perturbation, so we can neglect this, and here we identify qe with ql, or in the general case with the quantity, the background quantity q naught. So in that case we have that the Eulerian perturbation of the Lagrangian derivative with respect to time of q is given by the Lagrangian derivative of the Eulerian perturbation plus an additional term, which is the Eulerian perturbation of the velocity times the gradient of the background of the original quantity. Okay, so you see that Eulerian perturbation and Lagrangian time derivative do not commute. There are extra terms. You need to take into account extra term to account for the no, it's not really incompatible, but it's not, they simply do not commute. You have to be careful if you mix different perturbations, Lagrangian and Eulerian perturbations, and different time derivatives, Eulerian and Lagrangian ones, then you may get additional terms. Well, similarly, the operator delta, the Lagrangian perturbation, and d by dt and nabla do not commute. So keep that in mind. If you come across that situation, you have to calculate what is the relation between these quantities. As an example, which we might use later on, is the Eulerian velocity perturbation in relation to the Lagrangian displacement and to the Lagrangian velocity perturbation. So we would like to know the relation between the velocity perturbation either in the Eulerian sense or in the Lagrangian sense. So the Eulerian velocity perturbation is given by the Lagrangian velocity perturbation. Let's go up. Lagrangian velocity perturbation. This is the general form, the general relation we got. So we apply this. Delta q is equal to q tilde plus the Lagrangian displacement times the gradient. We apply this to the velocity. This means the Eulerian velocity perturbation is equal to the Lagrangian velocity perturbation minus delta r times the gradient, or the divergence of the velocity field. That's the better formulation. So from the general relation between Lagrangian and Eulerian, perturbation, we get that the Eulerian velocity perturbation is equal to the Lagrangian velocity perturbation minus Lagrangian displacement vector times nabla acting on the background velocity field v. Now we know the velocity is the Lagrangian derivative with respect to time of the position vector in the Lagrangian sense. Now we know delta and d by dt commute. So this is d by dt of the Lagrangian displacement. Minus, of course, this term is kept. Well, now we replace d by dt Lagrangian of the Lagrangian displacement by the relation between Lagrangian time derivative and Eulerian time derivative, which is d by dt plus velocity times nabla acting on delta r, on the Lagrangian displacement, and we are left with the final result of the relation between the velocity perturbation in the Eulerian sense related to the Lagrangian displacement. Eulerian velocity perturbation is d by dt in the Eulerian sense of the Lagrangian displacement plus velocity times nabla acting on the Lagrangian displacement delta r minus delta r times the nabla operator acting on the velocity field v. So this is a famous or often used relation between Eulerian velocity perturbations and Lagrangian displacement. Well, some authors even use mixture of Lagrangian and Eulerian perturbations just for convenience. Sometimes a variable might be better represented in the Eulerian formulation, and in other cases it might be considered in a more convenient way in the Lagrangian. So some authors use even mixture of Lagrangian and Eulerian perturbations. So far we have used only purely Lagrangian perturbations. We will, once we come to the non-radial pulsations, you will see that in some respect we also mix or have a mixture of both definitions of both approaches together. So I should warn you here, be careful whether you have Lagrangian displacement, Eulerian displacement, you have Lagrangian time derivatives, Eulerian time derivatives, you can easily get confused. Okay, that is a digression on a remark on the various perturbations. Well, now we are going to do the same as for the radial case. We will linearize the mechanical equations. However, contrary to the previous case, we will adopt the Eulerian point of view. Okay, we will use the mechanical equation in Eulerian form, and we will use Eulerian perturbations, contrary to the previous case where we have done it on the basis of the Lagrangian description. Well, first of all, in the Eulerian terms, or in the Eulerian momentum equation, we have this nonlinear term, which goes with velocity times nabla time acting on the velocity field, because we are starting from a hydrostatic star which has no velocity field. The velocity field of the unperturbed configuration is 0. This term will be a first order in the perturbations anyway. So we drop this term from the beginning because it will be of first order. And also we will replace here the 1 by tilde because we are assuming, or we are using Eulerian perturbations. So this quadratic term will be neglected. So the only term in the acceleration, well, dv by dt is Eulerian dv by dt, and v0 is 0. We have a hydrostatic configuration. Then the d by dt of the velocity which remains is simply the Eulerian derivative with respect to time of the velocity components. any other of these components or any other of the terms can be neglected because they are of second order, or we have zero velocity field in our hydrostatic configuration. Now, the right-hand side of the momentum equation consists of the pressure gradient and the gradient of the potential, the gravitational potential. So gravitational potential occurs linearly within our equations. So this is written as phi naught plus phi tilde. But for the unperturbed quantity, we have equilibrium between the pressure gradient and the potential. So this will cancel, the unperturbed term will cancel with the gradient of the pressure. Therefore, we have omitted it from the beginning. The only case or the only places where we have to introduce the perturbation is, first of all, we have to perturb in the Eulerian way the pressure. The right-hand side is 1 over rho dp by dr. This gives, first of all, this unperturbed term plus a perturbation of the pressure minus 1 over rho 0 times dp tilde over dr. We only have kept here the unperturbed term because otherwise we would have a second order term in the perturbations. Again, all second order terms in the perturbations are neglected, and then we have to perturb the 1 over the density, and we have this is multiplied with the quantities in the unperturbed system, because otherwise we will again get a higher order term, and we get a 1 over rho perturbed. 1 over rho perturbed gives rho tilde divided by rho squared, and the dp by dr, as a coefficient we keep the dp naught by dr. So this is the linearly perturbed first component of the momentum equation. Of course, we have now not only one component, because we consider three-dimensional perturbations which also depend on angle theta and phi, and of course we at the same time we do not only have one component of the velocity vector but three components. Clear? Okay, there is no stationary counterpart for the theta and phi component of the momentum equations, so they become rather simple. The left-hand side is similar, the acceleration is similar to the left-hand side of the radial component. So this is the Eulerian perturbation of the theta component, and the phi component differentiated with respect to time t in the Eulerian sense. Then we have, because there is no dependence of the pressure of the stationary model with respect to theta and phi, it's only the perturbation of the pressure with respect to theta and phi. So the term corresponding to that one would be cancelled, because dp naught by d phi and dp naught by d theta is 0. So we have the corresponding or the counterpart of this term with respect to theta and phi derivatives. So this is 1 over rho times the gradient of pressure with respect to theta and phi, and similarly also the gradient of the potential or its components in theta and phi directions is 1 over r d phi by d. Okay, this is the perturbation or the linearized version of our momentum equation. Well, the second equation which we need to consider for the mechanics is the continuity equation, of course. Well, the continuity equation, again, the velocity field in our stationary configuration you're interested, you can do it yourself. It's a little bit of algebra, simply saying rho is rho naught plus rho tilde. This means the density is split into the stationary and the stationary part and the perturbation, and then expand everything up to the velocity in the radial component times the gradient of the background model with respect to r. D rho naught by d theta and d phi is 0, therefore corresponding terms associated with the velocity components with theta and with phi are not present. And then we have the essentially the divergence of the velocity field essentially in terms of radial and the two tangential components of the velocity field. So this is linearized version of the mass conservation. And of course, now we have also to consider, in addition to these two equations, we have to consider the linearized of the potential, and we only need to keep the perturbations at any place. So this is, in principle, this is 4 pi g times rho naught plus rho tilde, but on the left-hand side, the Laplace operator on the stationary potential is 4 pi g times rho naught. So these two terms cancel, and we have left the linearized version, or the times the Eulerian density perturbation. So this is now a much more complicated version of the mechanical equations. We still have mass conservation and momentum equation, but in addition to that we have the equation for the gravitational potential. Okay, so what shall we do to get it back to time for the density and first order derivatives with respect to time for the velocities. So dvr tilde by dr, here we get another dvr tilde by dt, and here we get first order time derivatives with respect to the components. Second and third components of the momentum equations. So we have the expressions for dv theta tilde by dt and dv phi tilde by dt. We insert this and eliminate the velocity components v theta and v phi. What is the result then, which we are left with? Well, this is the form of the this is the form of the mass conservation equation. We have differentiated it. The v theta and v phi component by the respective components of the momentum equation. And then we are left with an equation containing only the density perturbation, the pressure perturbation, the potential variation, and the radial velocity components. We need to linearize the thermal equations. That means we need to linearize the energy conservation equation and the equation for energy transport. I'm sorry, it's now a little bit, it's a lot of algebra we need to go through. But in the end, everything will be nice and it will collapse again to some nice. Acting on the entropy S is given by the energy generation term minus the divergence of the flux, which describes the energy deposition. Here we certainly take into account the background model and we perturb everything in the usual way. Linearization means we expand it around the equilibrium and we neglect terms of order higher than 1. Okay, so the linearized version of the left the perturbed radial velocity component times the background entropy gradient. Well, this is now, first of all, the term rho times epsilon looks very much the same as in the radial case. There is no difference, but the divergence of the flux is now, of course, much more complicated because the divergence of the flux involves two terms with the radial, with the Eulerian perturbation of the radial component of the flux, and of course components which involve the theta and phi components of the flux. Okay, now we have used transport. This, of course, now does not have only one component, but it has 3 components. Oops, so this is a little bit of work, but we have done it immediately. I promise you we will. Okay, thanks. Radial temperature gradient in the background model, which needs to be accounted for. We have a perturbation, and we have the perturbation of the diffusion coefficient. The diffusion coefficient very much like the radial case. So this contributes via the perturbation of the opacity and via the perturbation count that for the background flux and the background temperature gradient, we have a special equation which needs to be satisfied separately. So this equation looks very much like the equation we have already had, but we have two additional equations, and we observe, or we take into account, can take the diffusion coefficient to be the unperturbed quantity. Everything here is given by the unperturbed diffusion coefficient, and only here, once we expand into first order, we relate the phi component of the what shall we do with it? We get rid of them actually. We get rid of the flux components in the theta and phi direction by inserting them into our energy conservation equation, which was the one above here. Let's given from or presented by the theta and phi component of the energy taking by applying the second and third component, and thereby we get rid of this equation and we get rid of the variables. Become smaller and smaller. So if we do this, just 2 minutes. Where is the mouse? Approach, we replace the perturbation of the radial component by the luminosity perturbation, and we end up with an equation, with an energy equation of the form which contains only the gradient of the luminosity perturbation, and then Eulerian temperature perturbation as in addition to what we had originally in our radial case, whereas the perturbation of the energy transport equation is almost identical to the radial case. These transport, whereas for the energy conservation, there is an additional term here involving theta and phi derivatives with respect to the temperature here. So these are the results for the thermal equations, and is we have the perturbed equation for the potential, and we have an equation for the perturbation of the momentum, for the combined momentum and mass conservation equation, which is this one. Okay, let's finish with the discussion of that this afternoon. So what we'll need to do, we want to give these equations, which seem to be rather complicated. It's a partial differential equation with respect to 3 spatially independent variables and 1 time variable, and we would like to reduce its complexity and its size down to a size which is similar to that which we got for the radial case. This will be done this afternoon, and then hopefully we finish with all that mathematical, nasty mathematical stuff here. Thank you very much.